Welcome back everyone. My name is Pedram and this is where we do machine learning codes and concepts. Let's get started. Alright, let's talk about the Python part of our module number 5, linear regression models, the machine learning approach. In the theory lecture, if you watched the previous video, we know that basically we talked about linear regression model, we compared with basically the econometric approach. Now we're doing the Python part for the machine learning approach. So we talked about linear regression, polynomial regression. We covered the concept of cross-validation and why we use it. And for example, in polynomial regression, we use cross-validation to tune the hyperparameter of the model, which was the polynomial degree, right? So we're going to replicate all these things in Python today. So without further ado, let's jump into it. So let's go to the GitHub folder for the course, Machine Learning USU, and then lectures and notes. Then go to module 5, and then there are two files here. So in this video, I'm going to cover the linear regression, and in the next one, we will cover the polynomial regression. All right, let's start with the linear regression. I'm going to do it in Google Colab because, at the end of this notebook, we're going to cover the same model using PyCaret, and it should be easier to install PyCaret in Google Colab for those of you who don't want to run PyCaret locally. So I'm going to open it in a new Colab notebook. Again, remember, this is my version. If you want to make sure that you have access to your version, you can edit it, you can play around with it, copy it to your own drive. So it's going to make a copy and open it there. Okay, if you remember in module 3, we talked about the same model, linear regression. And there we use a statsmodel package because it was basically built for regression analysis, for econometric analysis. It gives you nice, outputs, tables, calculating the t-stats, p-values, and lots of good performance metrics were basically reported automatically, right? But in scikit-learn, things are different. So, and by the end of this lecture, you'll realize that why scikit-learn is designed this way, because this is looking at the regression models from the econometric approach. You don't get access to the coefficients, names, t-stats, or p-values directly. You have to basically calculate them. There is no built-in function to give you, for example, the p-values when you're using a scikit-learn package. The reason is simply because we're not interested in those things in the machine learning approach. So again, I'm going to do this notebook and using scikit-learn, the machine learning approach, and at the very end of it, we're going to use PyCaret. Remember, PyCaret is that AutoML package that we're going to use for the project of the course, for example, running a horse race between different machine learning models. I encourage you to do things in scikit-learn because this is more flexible, you have more power, and then later on I'm going to tell you when and why should you use PyCaret. Okay, so let's start. So here's the agenda. I'm going to go ahead and let's import the relevant libraries. We're going to work with NumPy pandas, matplotlib, seaborn for visualization, and from scikit-learn, look at that. There's a module called linear models. Now, obviously, we're going to import our linear regression from our linear models, right? So this is a linear regression class. We're importing it from this module, scikit-learn dot linear model. So this is the module, okay? And in order to quickly compare the outputs of this regression with the econometric approach, we're going to import the statsmodels API as well. But remember, we don't need to do it for the machine learning approach. This is just for teaching purposes. Okay, and then let's go ahead and ignore the warnings. I'm going to set the random state to 100. You can set it to whatever number you want, but if you want to get the exact same numbers, make sure that your random state is the same, because when we're splitting the data into train and test set, that random number is going to be used there to split the data. So if your number is different, you're going to see different splits. All right, so the data set that we're going to work with is called Boston data set. So this is a very heavily used data set for predicting prices in Boston area neighborhood. It's a relatively old data set, but it is very good for benchmarking different machine learning models. We have to make some adjustments because let me actually show you what's going on here. If you go ahead and import this data set from the scikit-learn dataset module, so basically if you say scikit-learn.datasets import load Boston, so it's going to import that dataset. But it's going to give you an error. So this is, I think in the past couple of years, they noticed this kind of bias in the data set, and they want us not to use this data set, or if you're using it, not to use a variable b. So that's why we're going to get an error here. And basically this is, we're going to talk about this. So we want to make sure that we exclude this variable b, which is for, it has something to do with maybe race discrimination. So that's why we should be very careful. So I'm going to go ahead and comment this out. But the data set is very, very interesting. So I'm going to go ahead and drop this variable b and still use other variables, because we want to talk about categorical variables. We want to talk about ordinal encoding, one-hot encoding and things like that. I want to provide a notebook for you that you have every type of variables in it, and then once you master this notebook, you should be good to go for any other kind of regression analysis using scikit-learn. So I have put the basically clean version of this Boston dataset in my data folder for the course. So you can go ahead and import it from there. And now we have to go ahead and get rid of this variable b. Again, this b is because of racial discrimination, privacy, and biases. We're gonna remove this. We're gonna look into the name of the variables, and you'll see basically what are the other ones, right? So this is the head of the data set. All right, so again, for that reason, we're gonna drop variable b, which has something to do with the race discrimination, and now we're good to go. So this is our data set. The goal is to predict prices, and these are in the units of thousands of dollars. And the data set is old, from 1980 something, I guess, or 90s. And so $24,000, that was the price of the house. And these are the features, right? So we're going to look into all these things. So crime, for example, industrial, closing to the river, and age of the house, and etc. Okay. Okay, so let's do a quick EDA. First, starting by if there's any NA in the data. So we are going to use is NA. Look at the sum. No, all good. Is there any duplicates? No, all good. So again, just a reminder, here are the variables that we're interested. So this CRIM, crime, this is per capita crime rate by town, ZN, proportion of residential land, and industrial, proportion of non-residential business acres per town. CHAS or CHAS, this is Charles River's dummy variable. One means that, basically, if tracked bounds river, zero otherwise, right? And then this is some pollution variables, right? NOx, nitric oxide concentration. Well, the higher the worse, right, for the price of a house. Then we have average number of rooms per dwelling. We have age. We have, weighted distance to 5 Boston employment centers. This RAD, this is an important one. We're going to play around with it. This is the index of accessibility to radial highways. So this is going to be ordinal categorical. The higher, basically, the better. It has better access to highways. Then we have tax. We have, this is PT ratio, people-teacher ratio by town, and LSTAT. So LSTAT is a percentage of lower status of the population. Okay. So these are the variables. And then we can quickly look at the variable types. So they're all float. We know that a couple of them should be categorical. So at least this CHAS should be categorical. This RAT should be categorical. So we have to go ahead and quickly fix those types, right? You can look at the describe to get a sense of mean, median, average, Q1, Q3, and etc. So I'm going to leave this up to you because there's a lot more to cover. So I'm going to speed up through the EDA. And one quick, easy way to figure out if a variable should be numeric or categorical is to do a number of unique elements and look for single-digit numbers. So obviously this should be a categorical variable. This is a good candidate for categorical variable. You go ahead and read for example, read the documentation, and then you decide if it should be categorical, right? Or what type of categorical. So it seems that we don't need to make any changes to all the variables except the 2. So we're going to make, so this CHAS should be categorical and RAD should be ordinal categorical. Again, if you read the documentation, you will realize that, yeah, this is as I said earlier, this is index of accessibility to radial highways, right? The higher, the better. And then these are categories, but you can rank those categories. So that's why we call them ordinal categorical. So we have to do something about those things, right? So let's start by making some dummy variables. So first things first, we're going to make this our chast variable. We're going to change the type to category. Now, if I go ahead and look at the head of the data set again, so, and then we can look at the info. It should be category now, right? So if I go ahead and say df info, we already changed that chast to category, right? So this is taken care of. Let's look into the next one. And there are some other ways to do that, right? So I can change, well, actually, while I have changed it, when I have changed it to category, I can go ahead and make it a dummy variable. From pandas data, pandas package, we can import this get dummies attribute, method or function. And then basically we're going to say, hey, take this categorical variable and then make it into dummy variables, drop the first one to avoid that perfect collinearity thing, right? So basically, if I go ahead and do that, here's a data set, and then we have, where's our chast set? We have 0 1s, right? So for chast. Okay, so now we took care of the chast variable. Let's talk about our rad variable, which is supposed to be ordinal categorical, right? Again, ordinal encoding is a type of encoding for handling categorical data. Imagine we have, the data is something like this. High schoolers, bachelors, masters, and it's 1, 2, 3. Obviously, it is categorical and it is ordinal because the ordering, you can rank them. You can say, for example, master is higher than bachelor, bachelor is higher than high school. When we have something like this, we can use the ordinal encoder from the scikit-learn package. Okay, so as I said, this rad variable is basically the index for accessibility of radial highways. The higher, the better. Now, I highly encourage you, at least if you're a beginner with scikit-learn package, make sure you read the documentation for every single function that you're dealing with, right? So for example, here we're going to work with ordinal encoders. Again, I'm not going to go over the details, but I'll leave it up to you, that you just go ahead and at least read it once. So what is this ordinal encoder thing? What are the attributes and what are some examples? If you scroll down, you will always see some examples and you can play around with it. Okay. And of course, remember your best personal tutor is available, ChatGPT, Claude 2, Bard, you name it, right? Make sure you understand every single of it because this package is very, very well documented. And you can extensively benefit from conversation with these large language models. All of them are going to do a decent job when it comes to scikit-learn package. Okay, so this is our rad variable, and then we can look at the value counts and sort the index. Basically, it seems that we have, so the values that this variable is taking is 1, 2, 3, up to 8, and there's this weird number 24. And so we know that this is ordinal. We are going to go ahead and change the orders from 0 to 8. Make sure that this 24 is not going to make an impact anyways if you treat them as ordinal categorical, but we just want to make sure that this is the right name. And then, for example, we have 20 observations for this value, we have 110 observations for this value, and etc. Okay. So from scikit-learn pre-processing, so you're going to see me using this module a lot, for scaling the data, for pre-processing and things like that. So as the name suggests, this is for pre-processing. So from scikit-learn pre-processing, we're going to import ordinal encoder, and I'm going to create an object, right? So I call it ENC, basically my encoder, and then this is the ordinal encoder class. Okay, so this is my object. Now I can go ahead and fit transform the data. Remember, this is the original data. I'm going to fit transform using this object that I created. This is ordinal encoder. And I'm going to replace the rad variable with the new thing, with the transform version. So this should be straightforward. If you have any questions about any part of the code, please, just like the previous video that we went over, use ChatGPT, use Claude, use Bard, you name it. Okay, now this is the transform version. If I run the same code that we did in the previous cell, just look at the value count, sort index. Now it goes from 0 to 8. So we have 9 classes, right? And this is ordinal categorical. Okay, so that was, we're basically done. We changed our chast variable to dummy variable, and we changed our rad variable to categorical ordinal. But just for the sake of argument, I'm going to show you what if you wanted to treat this thing as a dummy variable. So how should you do that? Okay, So there is another way, there's another method in scikit-learn package. We from the pre-processing module, we can do one-hot encoding, right? So one-hot encoding is again another popular method to convert categorical data into binaries, zero ones. We can have more than two classes, right? And we can obviously use that one-hot encoding to create that more than two classes for us. Okay. So for example, I'm going to call this data frame df OHE, one-hot encoded. Right. Again, we're not going to use this for the rest of the notebook. This is just for the teaching purposes. I'm going to show you what if you wanted to use one-hot encoder to create your dummy variable, both for chas and for rad. Imagine you didn't want to treat rad as ordinal categorical. You just wanted to treat it as categorical, and then for 9 classes, you wanted to create 8 different basically dummy variables, right? How would you do that? Again, this is not a right approach to do it here, but again, what if you wanted to do it that way? If it is a binary variable, it really doesn't matter if you use get dummies or one-hot encoder. But if it is multiple classes, obviously you have to do one-hot encoding, right? All right, so let's see. We are going to import, we are going to make a copy of this data frame, import one-hot encoder. I'm going to call it OHE from pre-processing. So this is, we're just creating our own object. Again, it's pretty much the same. The pattern is the same when it comes to using these classes from scikit-learn package. I'm going to drop the first just to make sure that, again, we are avoiding that perfect collinearity thing. And this is typically what we do. And then I'm going to go ahead and say create this new variable chas, and it is a one-hot encoded version, the transformed version of the original variable chas, right? And we can go ahead and look at the data set. This is pretty much the same as what we did before. So this is going to be a dummy variable 0, 1. All right. Then off of that object that you call OHE, you can look at the categories, you can look at a bunch of other stuff, right? So for example, if you just simply type OHE dot control space, then it shows you what are the available attributes or methods off of this object, okay? All right, so let me go ahead and delete this. So for example, here we know that the categories are 0, 1, and yeah, that's good to know. And then, so this is the way we use one-hot encoded for creating a dummy variable for chas. Now, what if we have more than 2 classes? What if we had 9 classes in this example? I'm going to use the same one-hot encoder, dropping the first thing, and then now rad. This is a new one-hot encode transform data. I'm going to transform the original rad variable into a new one-hot encoded version. So what does that mean? Look at that. So this is the transform version. It means that if all of them are basically 0, and remember we had, let me actually show you the categories. So the categories are going to be 0, 1, 2, 3, all the way to the 8, right? So for example, this thing is going to be the one-hot encoded version of the first observation. If all of them are 0, so remember we dropped the first one, this means that it is our class 0, right? So for example, this is our class 1, this observation is class 1, this observation is class 1, and etc. So if well actually, let's look at the rad variable. Yeah, there you go. You see the first one, this is the original version, this is the ordinal categorical. It's 0, 1, 1, 2, and etc., right? If I make it into a dummy variable, one-hot encoded variable, so obviously we're using 8 numbers to represent any of those values, right? So if all of them are 0, it means that class is 0 because we dropped the first one. That's our base group. If the first one is 1, it means that this is class 1. So, and then if I look at the fourth one, it should be 2 and etc. So it's going to be 0, 0, 1 for this thing. All right, so hopefully it makes sense. If not, again, please make sure that you review these stuff on your own using ChatGPT and other helpers out there. Okay, so now I can get the columns of these rad variables. Remember, because we're going to turn this one single variable to 8 new ones, right? So let's give them proper names, right? So what are those names? So we can say, we can use this get feature names out. This is a method that we're going to say, hey, let's use this name for the beginning, input feature name. This is rad. If I use this one, so it's going to go ahead and create 8 different labels for me, right? Remember, it's starting from rad1, not rad0, because this is going to be dropped automatically, and that's our base group, right? So rad1 through rad8, now we have the names. We can just go ahead and put it in one nice column. Well, 8 columns. We can concatenate these things into one nice data frame. Sorry. Okay. So I'm going to create a new data frame, call it df1 hot encoder. Again, I'm going to update this. It's going to take this data frame and add 8 variables instead of the rad. Okay. So I'm going to say create this data frame based on this rad object that I created. Remember, this is my rad thing, right? And then these are the names. So let's do that. So let's use that data. These are the names. And of course, I'm going to concatenate these two data frames. And I need to remove this variable after when I make them dummy variables, right? Okay, let's go. So that's why I'm going to drop it. So let's go ahead and look at the data. Okay, that's pretty much it. So this is if you wanted to treat both chas and rad as categorical variables using one hot encoding. Chas is going to become one column because again, this is just a binary variable 0, 1. We drop 1, we come up with 1. Rad is going to become 8 new variables because it has 9 categories. We drop 1, we come up with 8 variables. Okay, hopefully this makes sense, right? But for our example, we're going to stick to this data frame, and where chas is dummy and then rad is ordinal categorical. We use ordinal encoder to make that happen. All right. Now our next task is to remove outliers, right? So let's go ahead and see how we can remove outliers. There are many different methods for removing outliers, but a very common one is to look into, plus minus some standard deviation, right? So typically we can do 3 standard deviation, 2 standard deviation, and etc. If you want to be more conservative, just do 3 standard deviation. So if the data is 3 standard deviation above or below the average, just drop them. And you know that 99.73% of the data is usually if it's within that range, right? Okay, so, and here's an important point. You should not apply removing outliers to categorical variables. So think about it, why? Okay. It shouldn't be difficult, but again, I want you to copy paste exact same prompt in one of your helpers and see what they suggest, right? Please get used to these kind of conversations with your large language models, and then it's going to explain to you why, for example, you should not do that. So the nature of categorical data obviously doesn't mean to, well, we cannot apply mathematical arithmetics to that or things like that. We're going to lose information, things like, just go ahead and just try it out and see what you get. But just remember, it doesn't make any sense to remove the outliers from the categorical variables, because imagine you have 3 classes, you have 4 classes, and you have 100 observations and 4 classes, and then there is one class that only shows up twice. So obviously, if you want to, well, let's say 1,000 observation and then 2 observations, so you can definitely say, okay, this is an outlier if you want to treat it as an outlier. But it doesn't make any sense, right? Because what if that class is something very important, but it's just underrepresented? That's it. So that's the nature of categorical variable. You should not remove that class from the data. All right, so for that reason, we don't do that. So the shape of the data set is going to be 506 observations, 13 features, and a target variable. So 12 features and a target variable. And now our task is to go ahead and remove the outliers. Remember, I'm going to go ahead and create categories. This is a list because I don't want to apply this outlier removers from the categorical variable. So I'm going to save this list. And then I'm going to say this is, so look at that. This, if I use df drop these 2 columns and then x is equal to 1, so make sure that these are columns and we're not in placing. So in place by default is false, so we're not replacing the original data set. This is how it's going to look like, right? So this is a data set without the categorical features. Okay, now I'm going to pick this and then apply the outlier removal to these continuous random variables, right? Okay, so for that, again, there are different ways you can do it from scratch. So you can calculate the mean and standard deviation and say, if use a bunch of filters, say, if it is less than -3 standard deviation, drop it. If it is greater than +3 standard deviation, drop it, and etc. Or we can use one of the basically functions from the scipy stats, right? No, stats, from scipy package, we can import stats, and then there you can simply do something like this. Stats dot, this is a function, and this is a data that you're passing. And simply if I say z-score less than 3, it's going to give you a bunch of true false, right? So, and I'm going to look at the absolute value. Just again, I just want to make sure that this is these are some true falses, right? So if I run this, it's going to look at the entire data frame. Remember, guys, what are we doing? This is what I'm putting here. Okay, it's going to look at the entire data frame, which is all continuous random variables, and check if the z-score is less than 3. That's it. So true, 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 false, and etc. So obviously, if it is false, we want to drop them. So how do we do that? So I'm going to go ahead and say, well, I can, off of this thing, off of this object, I can call dot all. So it's going to show me all of them, true. Well, basically, it's going to aggregate them for every single observation. For example, for observation 0, it's all true. It means that all of these things are less than 3 standard deviation. Observation 505, all true, and etc. Then if I simply go ahead and let's see why it's taking long. It shouldn't take that long. Okay. So then we're going to go ahead and sum these things. So if I go ahead and sum up all these things, it's going to count the number of observations that are within plus minus 3 standard deviation. Okay, it shouldn't take this long. Let me see. Automatic saving. Well, let me pause and come back when it's fixed. All right, so then there you go. These are true, false, and then basically if I go ahead and sum them, it's going to count them for me. So out of 506 observations, it seems that 469 of them are within the plus minus 3 standard deviation. Okay, so obviously if I change it to 2 standard deviation, then this number is going to decrease. Okay, so we're going to stick to that 3, and now, yeah. And now we are going to make sure that our new data frame is the one with where we remove all the outliers, right? So that's what we're going to do. We're going to say, basically, yeah, give me all these rows, these 469 rows. Okay. Now, if I look at the shape of the data set, this is going to be not 506, it's 469. So we remove the outliers. And this is our final data set that we're going to work with. Okay, cool. One last thing before we move on to the modeling part is just plotting the target variable. This is what I absolutely encourage you to always do. So here we're plotting the price. Not surprisingly, the housing price is usually right skewed. Here is also right skewed. If you were doing econometric, what would you do, right? What do you infer from this distribution, and what should you do with the target variable? Think about it. Well, one way to fix this, rightly skewed distribution is to use log transformation. And if I do log transformation, the odds that the classical linear model assumptions are not violated, it's gonna be basically higher, right? So that's why we in econometrics we are serious about this stuff. But in machine learning, we can go ahead and use the price variable. We can go ahead and use log price, but here, just to make sure that the target variable is interpretable, I'm gonna use price, okay? All right, we can look at the correlogram between, basically, this is a correlation which is going to show you the linear relationship between random variables. This is very important, guys. So I'm going to put the price at the very last row, and then the correlation between price and, for example, the crime rate, of course, is negative, positive, negative. It makes sense, right? So for example, this is a measure of basically income. Obviously, it's going to be negatively correlated. Well, this is LStat. Well, actually, let me remind you. This is percentage of lower status of the population, right? So it means that in that neighborhood, there are people with lower income. So the more that population, the lower the price of a house. Okay. Then we can look at bunch of, again, bunch of plots. Basically, your target variable versus other x's. Again, typically in a high-dimensional machine learning model, we don't do this. We don't have the luxury of observing things like this, because imagine what if we have millions of records of data? What if you have thousands of features? There's no way we can do that, right? But here, just for the sake of argument, I'm going to show it to you and say, let's investigate some relationship, right? So there's a clear relationship upward sloping between RM and price. There's a clear, it seems a downward nonlinear slope, nonlinear relationship between LSTAT and price, right? So actually, let me show, because we're going to use this one for our polynomial regression as well. So actually, this for the homework, you're gonna stick to this one. For the homework, I want you to work with this data set and try to fit a polynomial regression model into that and see if there's a nonlinear relationship between price and LSTAT. Okay. All right. So here's a so we are going to say that we're done with the EDA. So let's save it as a clean pickle file. Why pickle file? Because remember, if you do CSV doesn't have memory. It's going to forget all the variable change, the type variable changes that you did. So because we're going to use this data set later on for the homework, so we're going to save it as pickle file. Okay. So we are done with the EDA part, with the cleaning part, with pre-processing the data. Now let's go ahead and then split the data into train and test. So again, we're using scikit-learn package. So from scikit-learn, there's this model selection module. We're going to import train test split. Again, as I said earlier, if this is the first time you're seeing these things, please make sure that you read the documentation. So this is the documentation for train test split, and I'll just read. Just make sure you understand what it is and what are the attributes. And then if you scroll down, it's going to show you some examples. So for example, how can we do that? So we know that this is basically how we use it, train test split. And it seems that the output is going to be 4 things, right? X train, X test, Y train, Y test. So that's the way we're going to do it here as well. So my target variable is going to be price. My features are going to be everything but price, right? So we have to make sure input is equal to false, because we don't want to drop price from the data set, right? Okay, now as I said, this is the function we're going to use, train test split. It requires a bunch of stuff. The first thing is your features. The second thing is your target variable, and then you can put a test size or train size here. If I put test size equal to 20%, this is equivalent to if I use train size equal to 80%. That really doesn't matter which one you use. Again, look at the documentation. You can use, for example, here it's using train size, but it's using test size, but you can do train size as well, right? All right, then just to double check that it's doing its job correctly, and we can go ahead and calculate the length of the train set divided by the total length of the data. And it should be around 80%, right? Not exactly, but around 80%. Here, we're very good, 80%. And this is where the random state is going to come into place. Remember, we set the random state to be 100. And if you change that number, your splitting is going to be different. So what does that mean? It means that if I look at the X train, so this is observation number 344, observation 479. So remember, we have 400 something observations. We're going to pick 80% of them for the train set and 20% for the test set. If you change this random state, you're going to get different numbers here. But if you want to replicate this notebook exactly, make sure you use the same random state, which is 100. All right, our next task is to scale the features. So in the theory lecture, actually in module 4, when we were covering the machine learning fundamentals, at the very end of that theory lectures, we talked about feature scaling. Why do we need to do feature scaling? For regression analysis, for a model like this, simple linear regression model, it's not going to make any difference, right? Because, well, it's not going to make a huge difference. But for some machine learning models, it is going to be important. For example, if you're doing some distance, if you're calculating some distance between observations, like KNN models, we definitely need to scale features. But I'm going to save that conversation when we cover those models. But what if you want to scale the features? So if you remember, we have to scale the features using the train set, and when that scalar is fit or trained, we can apply that transformation to the test set, right? So, and this is what we're going to do. So we're going to use, so basically from scikit-learn pre-processing, I'm going to use standard scalar, and again, this is a class. And I'm going to create an object for that class. Now we have our object, so it's going to take some values and then scale them. That's it. So reminding you that this is a train set, and this is the shape of the train set, 375 and 12. Now I'm going to go ahead and create a new train set, call it xtrain_sc. This stands for scaled. and I'm going to use my object. This is my scalar, right? So scalar.fitTransform, look at that. This is important. This is where I want you to pay attention. I'm going to do fit transform to the train set. And remember, I'm not going to apply the scalar or the feature scalar to the categorical variable. It should also make sense, right? Because again, you can use ChatGPT and have a deeper conversation, but in a nutshell, it doesn't make any sense to scale the categorical variables, right? So for example, if your categories are three classes, red, green, blue, whatever, what does it mean to scale them? It doesn't make any difference, right? And so that's why we should not scale those. Actually, in some cases, when you have multiple classes, it's going to make things wrong. So you should not scale the categorical variables. Okay, so that's why we're dropping the categories. And look at that. I'm using fit transform, apply the fit transform to the train set, and only use the transform to the test set. So what does it mean? It means that only use the train set to calculate the parameters of this scalar. So what is the parameters of this scalar? So we're doing just standardization, average and standard deviation, right? So calculate the average and standard deviation of every single variable only in the train set. And then once you learn those parameters, use those parameters to scale the observations in the test set. We do that because we don't want to cheat, right? You want to make sure that even the scaling feature part of the machine learning is only applied to the train set. So we are not using anything from the test set, even for scaling the features of the model at any step of this process. We don't want to use any data from the test set. So that's why we're doing this. Okay. Now, if I look at the first two rows of the scaled version of the train set, by the way, pay attention. My train set used to be a data frame, nice pandas data frame, but when we apply this transformation, it's going to be a NumPy array. Okay, it's okay because scikit-learn models can handle NumPy array actually even better. So this is the first two rows. So for example, this observation, it's going to turn into this number, minus 0.54. What does it mean? It means that this guy, this house, this is a house. This house, when it comes to crime rate, the crime rate for this house is 54% below the average. So we know that we can interpret these numbers as well, right? And then, yeah, you get the idea. All right, so this is a train set. We can look at the shape of the train set. Right now, it is 10. Remember, it used to be 12, but we removed those categories. We have to add them back, right? So this is exactly what we're going to do next. So we're going to add back those two categories to the train set, which is scaled, right? So how do we do that? It's simple. So we're going to use basically we're going to create two data frame and then concatenate them. So the first one is X-train scale. So this is a nice data frame. We use pandas data frame. This is a data, and the columns are simply just the name of the columns, right? It should be pretty straightforward. And then we are going to add these two categories, these two variables to the data set, to the scale version. So that's what we're doing. I'm going to go ahead and reset the index to just make sure that, instead of seeing 344, 479, we want to see 0, 1, 2, 3. So that's why we're doing the reset index thing. Okay. So if you go ahead and do that, this is our new X-train scaled version of the data. All right, and it should be. Let me see. It keeps giving me this error that this notebook is running. There's another version somewhere else being run. I don't think so. Yeah. Well, if it bothers us, I'm gonna go ahead and check it out. But for now, let's move on. Hey, typically this should be faster. All right, so. Again, this is the shape of the scaled version of the train set. 375 observations, 12 features, awesome. Remember, we did not change, we did not scale these features. It doesn't make any sense to scale the categorical features. All right, we're going to do exact same thing for the test set. So we just replace the trains with tests, and that's it. Now this is our test set data set. Now we are ready. So we have two data sets, train, test, 375 observation for train, 94 for test. Now let's get into the machine learning part of linear regression using scikit-learn. It should be pretty straightforward. Okay, so as I said, we are going to run this regression using scikit-learn package. From scikit-learn linear model, we can import linear regression class. And if you go over these functions or classes in Google Colab, the cool thing is that you can go ahead and look at the source code. You can look at the documentation. So for example, if I just stay here and then go open in a new tab. So this is a documentation of that basically linear regression class, right? So yeah, so there are some default values. So for example, by default, the intercept is, there, and then we can look at the documentation, and if you scroll down always, you're going to see some examples. It should be pretty straightforward to using it, right? We're going to say, hey, this is my model. I'm going to fit. This is X features, Y target variable. That's it. And then this one line of code is going to do the job for us. Okay. So let's go ahead and import that module, that class. I'm going to create an object, call it regression model, whatever you can call it. And now I know that inside this object, there's a linear regression model. And as I said, we're going to apply this linear regression to our scaled version of the train set and the features and the target variable. Okay. And this part, again, guys, don't get too much, worried about how to code these things, at least these days, right? Because I want you to focus on the theory part more compared to this, because let me actually show you something. So for example, show me a simple example of linear regression model using sklearn in Python, right? So it should be super easy. This is basically it's creating a random data set for you, some X's and Y's, and then that's it. Model, linear regression, model fit, and then you can make some predictions. So we're using predict. And if you don't understand these things, you can say, hey, explain it line by line, right? So don't get super worried about, okay, can I do it in Python? How should I do it in Python? Of course, read the documentation, understand the details, and then use ChatGPT or any other large language model to help you out with the coding part, okay? So yeah, we have a model, we fit the model using a train set. Now we are ready to make some predictions. So we're going to say, hey, from this object that we created, use predict, and we're going to predict on the test set. So these are our Y hats. So the Y hats are going to be a bunch of numbers. So for example, actually, let's put it in a nice table. So I'm going to go ahead and create a test prediction table. So this is a data frame, and I'm going to see actuals, which is, I'm using a dictionary, right? So this is the fastest way to create a data frame in Python, by the way. Nice way, you can have the column names and the values. So that's why we're using dictionaries. So actuals, Y test, predictions, Y hat that we just created. And then we can do residuals, Y minus Y hat. And ordering matters, right? Remember, Y minus Y hat, not Y hat minus Y. Okay, there we go. This is our nice data frame for predictions and actuals. So observation 93 in the test sets, the price was 25,000. We predicted to be 28,000-ish. So the model is overshooting. That's why the residual is negative, right? Okay, we can get access to some of the components of this object that we trained, right? This model that we trained, so reg model. If I go ahead and try, for example, reg model and then control space, and it's going to give me what are available. So I can get access to the coefficients, feature names. I can use the fit. Yeah, you get the idea. I can look at the intercept and et cetera, right? You can change the parameters if you want. You can look at we're going to talk about the score. This is the R score of the model, right? So let's look into the coefficients, for example. Coefficients, yeah, this is, the coefficient of the first variable, coefficient of the second variable, and et cetera, right? And actually, yeah, and this is interesting, right? Because remember, in the econometric approach, we just ran one line of code and we had access to all the coefficient, t-stat, p-values. But it seems that in scikit-learn, it's kind of pain, why they didn't do an inbuilt function for that nice summary output. Simply because we don't care that much about that interpretability in machine learning. So that's why these packages are fundamentally different. And hopefully you get the difference now. I can look at the intercept. So the intercept is this number. So again, this coefficient is going to only give me the coefficients. This should be 12 numbers because we have 12 features. Then an intercept, we can again remind you what are the columns. If you want to create the nice table or data frame for coefficients, you can run something like this. Hey, create a data frame. Features are basically all the columns, and these are the column names. And so just put it this way, right? And then coefficients, we're going to use the coefficient from the model. Let's round it up to 4 digits. Okay, so this is our synthetic regression summary that we put together. Okay. All right, so if let it run. So as you can see, there's going to be a simple table looking at the coefficients and basically the values. It shouldn't, from your end, it shouldn't take that long. I don't know what's going on here. Maybe there's an internet connection or something, but it shouldn't. This is a super simple model. It shouldn't take that long. Okay. So while it's working out, it failed. Let's see. Okay, let me save this. And okay, let me pause the recording and fix this. Yeah, let me actually go ahead because it keeps telling me that there's another session running, which I doubt, because when I look at this session, this is the only session. So I'm going to go ahead and restart this session. You know, let's restart runtime. Yeah, and I'm going to go ahead and run everything before this cell. So it should be fast. Yeah, so while it's working on it, let me see. Yeah, I think the plots is going to take a little longer, the heat maps, and yeah, this is, and remember, this is only 500-ish observations, right? So that's why we usually don't do things like this in machine learning approach, because again, we are dealing with thousands of records of data and then hundreds of features. And as you can see, this is taking a little long for a simple task like this. So let alone if we wanted to work with thousands of data. And again, we don't typically do that. All right, so yeah, let's actually comment this out. This should be good. Yeah, let's run these things. Okay, this should be fast. As I said, this should be fast. Okay, these are the coefficients. Now let's talk about some evaluation metrics, right? So for example, what are those things for regression? We talked about in the theory lecture. We can look into R-square, MSE, RMSE, adjusted R-square, AIC-BIC. We are not going to look into adjusted R-square, AIC-BIC, because if you watch the theory lecture, we're going to do cross-validation to just make sure that we are controlling for that bias variance trade-off, and then we don't need to be worried about addition of those extra features that's going to increase the R-score no matter what in the train set. But it's going to increase it in the train set. In test set, that's not always the case. So that's why we're not worried about reporting these things in regression machine learning. Typically we work with RMSE. That's basically one of the best metrics that we use for training the model. There is only one thing that's built in, one metric that's built in this regression model object, which is a score. So in regression analysis, when you see score, by default, it's going to calculate your R-score. If it is classification problem, by default, it's going to calculate accuracy. So this is a regression problem. So this is going to be our R-score in the train set, because I'm using train set, X and Y in the train set, and I can compare it to the performance in the test set. So it seems that in the train set, we're doing 73% R-score, in the test set, 72%. Okay, they're not that different. So I think probably this is doing a good job already. There's no hyperparameters here to tune, so we're going to take it. Okay. We're going to say, okay, this is the model. Let's stick with that. Of course, you can go ahead and do some feature engineering, add, remove variables, add the quadratic version, add interaction, etc. But again, in machine learning, we're going to look into those nonlinear relationships simply by using auto models, not linear regression. Okay, so as a reminder, so here is our y hat and residuals. We can go ahead and calculate the mean squared error or root mean squared error manually, right? So from this nice table, let's take the residual. If I square them, take the average, this is my mean squared error. That's it. What is the unit of this? This is $1,000 to the power of 2. So it doesn't make any sense. So that's why we take the square root. So now this makes sense. So 4.1 means $4,000. Because remember that your target variable, that's the unit of the target variable. So if it is 25, means 25,000. Okay. So our next task is to do cross-validation. From the theory lecture, we remember we do cross-validation for two things. First of all, for tuning the hyperparameters. In general, we can call it model architecture selection. Secondly, for doing a fair estimate of the performance of the model in the test set. So this is a simple linear regression model. There is no hyperparameter, so we're not going to do cross-validation for this purposes, for the tuning the hyperparameter. However, we can go ahead and use cross-validation to estimate these numbers. This number to estimate this number. Remember, this is the performance of the model in the test set, which is 72.3% R-squared or 4.10. But what if you don't have access to the test set and you want to get a fair estimate of this performance in the test set, right? So that's why we're going to do cross-validation. Let's go ahead and do that. So when it comes to cross-validation, there's this nice function that you can call from the scikit-learn model selection module. It's called cross-val score. And actually, I'm going to go ahead and show you, well, I'm going to import from scikit-learn, I'm going to import metrics and cross-val score. So what are these metrics? So if you want to see the whole list of metrics available in scikit-learn, you can run this line. Scikit-learn metrics, show me all the scorers. By the way, we call these metrics scorers because they're going to score your model at the end of the day. So that's why you can have your own scorer as well. So for example, if it is not in this list, you can create your own scorer, but that's a little more advanced. For those of you who are interested, I encourage you to just Google it, use ChatGPT and help you out with that. All right, so these are available scorers that comes with scikit-learn package. And as you can see, there's a ton of them. Lots of them are for classification and a bunch of them are for regression analysis. For example, accuracy, F1, these are all for classification. For regression analysis, remember we were interested in, for example, R-square. So let's see, yes, we have R-square. We were interested in mean squared error. As you can see, there is no mean squared error, but there is negative mean squared error. So I don't know, negative mean squared error. The reason that we see the negative version here is that these metrics are all based on a maximization problem. So we want to maximize accuracy. We want to maximize F1 score. We want to maximize R squared, right? But we want to minimize mean squared error. So if you want to minimize something, if you take a negative version of that, you can maximize it. So that's why, in order to make sure that we are just using in one consistent optimization problem, which is a maximization here, we're going to work with negative mean squared errors. All right. So, and it's super simple to do that. Again, if you just go over this and wait a second, you can look at the documentation and see what's inside, or simply, I'm repeating myself a ton, I know, but simply use Claude, Bard, ChatGPT, because these packages are very, very well documented, and it's going to help you a ton in terms of doing things, right? So for example, simply type, how can I do cross-validation using scikit-learn? It's going to generate the entire thing for you. Okay. So let's replicate, well, actually, let's estimate this number. Let me go back. There's this R squared, 72.3% in the test set. Let's use the train set with cross-validation to estimate this number, to get a fair estimate for this number, right? So that's the agenda. So I'm going to go ahead and create this R squared, which is a cross-validation score. You have to give it an estimator. We're going to give it simple linear regression model. You have to give it X and Y. So we're going to pass the train set. Be careful, the train set, not the test set, because it doesn't make any sense to pass the test set here. You want to use train set, make it to K-fold, and then get an estimate for the performance in the test set. How many folds? 5. CV, this is cross-validation number of folds, 5. And scoring, this is your scoring metric. So here we're going to pick R squared. If I run this, then in this R squared object that I created, there are going to be 5 numbers. Why 5? Because it is 5-fold. So it's going to use the training data set randomly each time. It's going to use 4-fold of it and make a prediction for the 5th fold, right? So this is 1 number, 2nd number, 3rd, 4th, and 5th. That's why we have 5 numbers. If you aggregate those things, actually we had a slide for that, right? So let me see. Well, actually, we didn't talk about it in the previous class, but it was in the fundamental part, right? So if you take the average, it's going to basically report the fair estimate of the performance of the model in the test set. So if you only leverage the train set and hey, say, let's use cross-validation a fair estimate of the performance of the model in the test set is 68.4. Remember, the actual number in the test set was 72-ish%. So we're pretty close. Okay, cool. And we can definitely do mean squared error, the same story. So, and the reason I'm using this negative sign here, because remember guys, if I do cross-val score, same estimator, x, y, and then scoring is negative mean squared error. So that's why the output of this thing is going to be a bunch of, here actually we're using tenfold. It's going to be 10 negative numbers. So I'm going to multiply it by a minus, so I get a positive number. So I have mean squared error. So these are 10 numbers because we have tenfolds. You can take the average. Why did I use 10, not 5? It really doesn't matter. You can do 5. But we typically do 5 and 10, and that's it. Well, of course, if you do more folds, it's going to take longer. But this data set is nothing that's small, and then we can afford to do 20 folds as well. There's some nuances there. If you're curious, please make sure you just read the documentation more carefully, or just Google it around, or just use your personal tutor. All right. So this is a fair estimate of the performance, the MSE in the test set 23.2. We can do the same thing. If I take the square root, we can do the same thing for RMSEs. And so this is a fair estimate of the RMSE in the test set. Again, one last time, what was the RMSE in the test set? It was 4.10. We estimated this number to be 4.6. All right. So that's it. That was machine learning using scikit-learn package, machine learning, linear regression machine learning approach, right? Just a quick reminder, how do we do things in the econometric approach? Again, this is going to be super fast. We could do stats model, right? From stats model, using the same test and train set, but I'm adding the constant. And then now I'm going to use from stat model API, OLS, basically your Y and X, and just do a model fit, look at the summary stat. So as you can see, it's a lot easier to extract information using econometric approach, right? We have access to the standard errors, t-stat, p-values, lots of good metrics here, right? So why do we do machine learning approach then? Because in machine learning, the only thing that matters for us are these numbers, well, the performance of the model in the test set or the cross-validated version. Okay, so we care about the predictability. We don't care that much about the coefficients. That's why we don't do it this way. And even if we want to do interpretable machine learning, there are better models out there that we're going to talk about them later in the course. So that's pretty much it in a nutshell. Yeah, and just look at that. The coefficients should be pretty much the same as what we had using scikit-learn package. So for example, for crime, it is minus 0.00096. It was minus 0.00096. And it took us a while to get into this simple column using scikit-learn. All right, so now the next thing to do is to basically run linear regression using PyCaret package instead of scikit-learn. Okay, let's do things in PyCaret. Again, for the rest of the semester, I will be focusing mostly on scikit-learn because that's the right way to do that. It's more flexible, especially when it comes to tuning hyperparameters. You have more degrees of freedom. But because at the end of the day, you want to do a project and run a horse race between 20 different models, maybe PyCaret is a good start. So you can start with PyCaret, compare all those models, and then pick the one that is the winner, and then use scikit-learn to dig deeper into that specific model, right? So the PyCaret as of now, which is September 2023, it's 3.0 version. Actually, it's 3.1, I guess. Here's the documentation. It has a very relatively well documentation, but it's a lot. It's a lot to cover, and then I think I have a couple of other videos that I talk about the details of PyCaret, and hopefully you have watched them by now, and so I'm not going to talk about all the details here, but at the very high level, with what we do with PyCaret is that we're going to set up some experiments, and then we can go ahead and create model, we can do compare models, and that's it. So these are basically the ones that we need for doing basic PyCaret. When you're setting things up, setting the experiment, there are tons of things you can play around, right? So you can look at how to handle outliers, how to handle categorical variables, things like that, right? There are lots of things you can go through, and of course, this is beyond the scope of what we're covering right now. But I highly encourage you to, it's a powerful package. It's a powerful package, and we can use it for benchmarking for sure. So I'm going to go ahead and install it. If you have it on your local computer, you don't need to install it every single time. But if you're running it on Google Colab, just like me, you have to do pip install PyCaret. Okay. If you do pip install PyCaret, it's going to install the light version. So what I mean by that? So the light version does not come with all the, does not come with all the models available, right? So for example, down the road in the course, we're going to do XGBoost, we're going to do CatBoost or LightGBM. So if you just import PyCaret, you don't have access to those models, right? Or for example, you don't have access to some specific tuners or parallel processing and things like that. So that's why we're going to keep it simple for now, but through the end of the semester that we're doing XGBoost, we can go ahead and install the full version. So for installing the full version, we can do something like this. But especially if you're doing it in Google Colab, don't install the full version yet because it's going to take a lot longer. So this thing is just, let me see. Okay, it's done. So it took a couple of minutes, maybe less than that, to install the light version. So every single time that you're doing PyCaret in Google Colab, you have to install it because it's not already installed in Google Colab. Why should it be? All right. So now let's check the version. It's 3.1. Again, by the time that you're watching this, who knows, maybe the next release is there. But let me remind you the data set. So doing things in PyCaret is super simple. So let's look into that. This is a data frame. We are going to import regression. From the regression module of the PyCaret, we're going to import everything. Okay. This everything means everything you saw here. Setup, create model, compare models, everything. So we already imported all those things by just running this line, right? Now I can do setup. So what is the setup? I'm setting up an experiment. So give me the data frame. What is your target variable? Price. This is just for randomization. Session ID, you can use whatever number. How do you want to split the data? Train size, 80%. So this is what we did, right? What is your folding strategy? There are different folding strategies, by the way. You can take a look there. But we're going to do k-fold strategy, right? How many folds do you want? 5. Do you want to normalize the data? This is basically the pre-processing thing. You say true. Do you want to what is your normalization method? We say z-score. So I try to make it as consistent as possible to what we did manually, right? So by just running this line of code, it's going to set up the experiment for us. So it's going to go over this data set and then do all these things under the hood. And then now the experiment is ready. We can go ahead and run models based on that, right? So if I just simply do models, open close parentheses, it's going to tell me what are the available models in the light version of PyCaret, right? Well, I installed interesting. I have XGBoost in LightGBM and DOMA. Interesting. Yeah, we didn't install the full version. Yeah, I have to dig deeper, but anyway, so it seems that even in this light version, they added the XGBoost. So I have to check the latest documentation. But the good news is that we have all these things. But it seems that, yeah, we don't have access to the CatBoost here. Yeah, so probably that's in the full version. So actually it's a cool thing because now if you do the light version, the XGBoost is going to be there. And this is one of the most powerful models there. So you don't need to install the full version to get access to that. So this is going to make our job a lot easier for the machine learning course. For the deep learning course, we are going to cover some more advanced models as well, including CatBoost or ensembling techniques and things like that. Okay, that's it. So these are the models. Now I can go ahead and create my own model. I can say linear regression. This stands for linear regression. I use the create model, the function. What is the estimator? LR. What are we doing here? You don't get overwhelmed. Again, if you just do ChatGPT or just simply do documentation, it should be straightforward. So for example, go to the create model. What do you need? Here's an example. That's it. So create model LR. This is basically, and then you can look at the other abbreviation. LR stands for linear regression, lasso, reach. These are the ones that we're going to cover next module, and etc. Okay. All right. So then I'm going to go ahead and create my linear regression model. So, and as you can see, it's gonna use 5 folds because this is how we set up the environment. We said let's do it 5 folds, right? 5 folds. Okay. So, and these are the performance, look at that, these are by default reported. We don't need to do it manually. So MAE, MSE, root mean squared error, and R squared, MAPE, and RMSLE, they are all reported, and for each fold, right? And then we look at the average. So, and yeah, this is, and we also have access to the standard deviation. So this is cool. So for example, remember we did the cross-validated version using scikit-learn package. We get to 69-ish%. So these numbers are pretty close. So 70% here. Obviously, the random initialization is going to make some changes, right? So 70%, 69%, we did it manually. Okay, pretty close. And then you can tune this model. You can tune any model using PyCaret by calling this simple function, tune model. So you have trained the model, I call it LR, I'm going to go ahead and tune it. Here, if I run this line, nothing is going to change. Look at that. You are going to get exact same numbers. Why? Because there's no hyperparameter here. So this is a simple linear regression model. There's no hyperparameter. There's nothing to optimize there. So you get this exact same thing. Then the last thing about PyCaret, which makes it super powerful, and that's its visualization capabilities, right? Because you can visualize lots of cool stuff using PyCaret for any kind of model, right? Because remember, I have lots of models here. I don't know, 20, 25 models here. I can go ahead and plot, I can run one line of code, which is compare models. We're not going to do it yet because you're not familiar with all those models. But if I do compare models, and if I just run this simple line of code, it's going to go ahead and compare all these 25 models and then calculate. Of course, it's going to take some time depending on the size of the data set, and report all of those things for every single model. Okay, so that's powerful. And then more interestingly, you have access to the plots for every single model, right? So for example, this is my model LR, so I'm going to plot the residuals. So by the way, there are lots of things you can plot. You can plot the residuals, which is obviously a residual plot. You can look at the errors. This is y hat. You can look at the learning curve. We know what it is from the theory lecture. We were going to talk about it. You can look at the feature importance. This is something we're going to look into later on. And yeah, if it is decision trees, you can look at the tree and etc. Okay, so cool. So if I run this simple line, it's going to plot the residuals for me. Again, R score in the train set 72, in a test set 74 here. Yeah, it's doing a decent job. This is the normality. This is the distribution of the residuals in the train and test set. It's, well, we can say it's relatively normal. And if you're looking at it from the econometric perspective, this matters a ton, right? Because if it is not normal, one of the assumptions is violated. Your numbers are, basically sketchy. You cannot trust them. Then we can look at the error plot. This is y hat. If ideal world, it should line up all across this identity. Well, basically this diagonal thing. We are a little off there, but again, we're doing a decent job. We can look at the learning curve. So this is also very powerful. Guys, if I wanted to do this thing from scratch, it was easily tens of lines of code in Python. But now we have one line of code and we can do it PyCaret. And I think it's not complicated, right? So we can say, hey, for example, let me help me plot the learning curve for this regression model using scalar. Okay, we're not going to use PyCaret, so it's gonna generate some code for us. Okay, so while it's working on it, I'm gonna go back to this and we're gonna check it out. So this is a learning curve. If you, from the theory lecture, you should know that the performance, this is a number of observations in a train set. So as this number of observations increase, obviously the performance of the model in the train set is going to get worse, because if I have only one observation, I start from R squared 100%, right? 1. And then if we increase more observation, the train set performance is going to decrease, but the cross-validated version is going to increase. Okay, so this is great, right? This is actually great because it seems that these two curves are converging. So it means that I'm not going to better off having more observations in this data set. So basically we are close to 72-ish%. And they are converging. And one other thing that I could do is if I can compare it with a benchmark. If a benchmark is 65-ish and this is the model, this is a perfect model, I'm going to take it. Okay. All right. So the very last thing is make some prediction. Again, making prediction using PyCaret cannot be easier. I'm going to say These are PyCaret predictions. Predict model, again, what it is, just go ahead and read the documentation. There should be predict model somewhere. Yeah, predict model. And then pass the model. So by just running this simple line, it's going to give you some interesting outputs. First of all, it's going to give you the original data and the prediction. So this is your prediction label, okay? And you can get access to them by extracting the second element of this object, right? And yeah, and you have see the performance of the model in the test set as well. Okay, cool. And yeah, just be aware, this object that you created, LR, because it is written based on scikit-learn package, it has all the features that you can extract in the scikit-learn package. So for example, if I do lr.coefficient underscore, it's going to give me the coefficients. All right. So to wrap it up, what I want you to know about PyCaret is that actually it's built on top of scikit-learn. So all the models that we're using is there. Actually, for those of you who are curious in basically looking at the source code of PyCaret, I absolutely encourage you to check the PyCaret model container. This is under GitHub. So this is a model container. This is going to be a little more advanced. So if you're not following this, totally fine. But if you're curious, what are the models inside the PyCaret, you can go to the container folder under GitHub and then go to, for example, regression, okay? And then search for the model name. So for example, if I do LR, this is linear regression. So as you can see, it's using scikit-learn and scikit-learnx packages. And then yeah, this is basically, this LR, this is literally from scikit-learn. This is what we did manually, right? From scikit-learn linear model import linear regression. And if there is some tuning parameters, we're going to talk about them in the next modules. This is a simple model. There's no hyperparameters. You're not using any tuning arguments, right? Okay, so yeah, we're going to cover all these things later on in the semester. Talk about different models, etc. So for example, you can do KNN regression. Just search for KNN and see what is the model. So the model is coming from basically scikit-learn again. Scikit-learn neighbors, import k-neighbors, regressor. All right, so that was pretty much it. I know it was long, but we are going to become more efficient as we go through the semester. So we're not going to repeat, for example, how to do cross-validation, how to do splitting the data. So just bear with me, and then this thing is going to get better and better. Don't expect yourself to become an expert by after watching this video. Give yourself a little time, and you will get there. Don't worry. Take care.